Okay, so our final severe weather video talks about thunderstorm features. There's basically a lot of different zones or parts of a thunderstorm that you'll recognize as very consistent and common with various thunderstorms as they come and go throughout the summertime. And so what I want you to be aware of is some of those features, what they represent, how they form, why they're there, and then how they can be used to help us understand how the thunderstorm works. So you should have a handout that has this diagram on it, and again sort of looks at a large-scale thunderstorm in its mature stage, in that mature cumulus stage. This is at that sort of heart of the storm's most active time frame, and this zooms out a little bit further, so it shows us really the whole cloud more in detail, and includes a little tornado sticking out the bottom there, as you'll see. So what I want to have you do then is just kind of label on here a few different regions or parts that are most key and consistent, and have you label them right on the page. If you want to try to add notes around that, you can. It kind of depends on how small you write. But if you want to at least label them on there, and then you can take the notes somewhere else if you rather have more space. Probably better if you don't put them on the back, because it saves you on flipping. It saves you on flipping back and forth, so you don't have to go back and forth to see what things are. Put it on a different page and you'll be a little bit better off. So the first feature I've mentioned to you several times and shown you pictures of in the past, and that's an anvil top. When we're looking at a thunderstorm, it flattens out when it reaches the tropopause. And so when you see an anvil top on there, the idea is that it represents an anvil, like you've seen maybe in an old cartoon. Wile E. Coyote was always using anvils, and it was used in blacksmithing. So if you see someone working on blacksmithing techniques today, or if you see a reenactment of an old blacksmith, you might see someone working on these large iron stools, basically, or platforms that they can use to pound on heated metal to make horseshoes or spears or whatever they might be making. So an anvil top cloud reminded someone of an anvil perhaps in their own blacksmith shop and said, hey, that cloud looks like an anvil, and ever since then they've called it that. What happens is the atmosphere is now stabilized above that height and the cloud can go no further up, and so the cloud starts to spread out horizontally instead. The next feature you'll notice on a thunderstorm is called the overshooting top. Now this is really only obvious if you are looking at a cloud from somewhat of a distance. If the storm cloud is directly over you, you can't see the top of the storm cloud. You're only seeing the bottom. So when the storm is off on the horizon or moving across the north, and perhaps north of Bismarck or south of Bismarck, or hasn't even reached us yet, then you can see it far enough away to where you'll pick out the fact that it might have a lumpy top. There's a flat cloud top there, yes, but then there's a little lumpy top on top of it. That's called the overshooting top. When you see an overshooting top, a lumpy sort of irregular top on a normal flat anvil surface up there, that's not a good sign if you're scared of severe weather or if you might be at risk of being in the storm's path. Because what it means is that the updrafts in the cloud are so strong, so fast, and so significant that they're actually breaking through the tropopause slightly and causing the cloud to sort of spill up into the stratosphere. That is an incredibly strong storm that has a lot of updraft potential, has a lot of power, and that means it can volley ice chunks up in there and grow them into huge ice and hailstones, which I'll show you some pictures of in a minute, or it could even kick up a tornado. So when you see an overshooting top and that breaking through the normally flat surface up there, that's a sign of a very significant thunderstorm. And again, only storm chasers would be thrilled to see that. This is what a picture of an overshooting top looks like as taken from a view of out a plane window. You can see here in the distance there's a sort of flattened top on this cloud, and then right there in the middle of it some parts of it have broken through and are spilling over into the stratosphere. This plane looks to be flying at approximately the height of the tropopause, maybe a little bit above it, and so you're looking sort of right across to that height and seeing what a tropopause sort of boundary that's being broken through starts to look like. In the foreground here, as you look lower into the nearer clouds, it's a pretty consistent, steady layer of clouds across in the near ground as well. And the wing of the plane, of course, out the distance there. The next feature here is called a Mammatus cloud. Mammatus clouds are found usually along the edge of the cloud somewhere. It could be really any place. In fact, they can form high in the clouds or low in a number of different locations. And what you'll notice about the Mammatus cloud is they have a very round, sort of sagging bottom on them. This round bottom of the cloud is usually many little lumps that seem to hang downward, and they're kind of found in bunches, almost like grapes hanging in a bunch. This is a sign that there's a ton of moisture in this cloud. In fact, it tends to show that the updraft is still holding that water up in the atmosphere. It's holding that rain and water in the air in the cloud, but man, it really wants to fall. It's so heavy that it's almost sort of pushing its way down out of the cloud. Well, you can imagine the bottom of the cloud is sort of popping like a water balloon, and the water just kind of bursts all out of there when it can't stand it anymore. Now, clouds don't have skin like a balloon or anything, but when you see these Mammatus clouds, it's a sign that there's some substantial weather and moisture up there. Typically a sign of some very heavy rainfall for someone coming up soon. Now this is what a Mammatus cloud sort of area might look like from the ground. You can see a whole bunch of lumps sort of right here across the whole sky. And they're very rounded on the bottoms. They look as though they're little sort of droplets up there. It almost reminds me of a little bit of a lava lamp surface where there's kind of this round, sort of smooth round bottom. And that's what a Mammatus cloud looks like. Usually, again, hanging in many bunches. And they're not necessarily a sign of a severe storm in terms of hail or a tornado, but of heavy rain. And maybe not here, but somewhere that rain's going to probably fall and dump a lot of water on somebody. This isn't so much a feature of the storm as it's just a region to be aware of. That, again, as I showed you in the last one, on that second stage of the thunderstorm's development, there's this area where the rain is heaviest. Right here where the warm air flowing in and the cold air flowing out sort of meet, just behind that there's a zone in here where the sweet spot is for the heaviest of rain. Behind the front edge of the cold downdrafts, and right where those warm air updrafts are starting to form, it begins there in the cold area, the heaviest downfall. Possibly some hail hiding out in there too. Now, if we look at this cloud sort of sliced through, from side to side and look at that cross section sliced out of the middle of it, we'd start to see a little bit more clear picture of where those hailstones can start to look at. And I'll show you what that picture looks like here too. The other term I'll mention to you here now, it doesn't necessarily have a place to label in the cloud so much. I guess if I had to point at a place for accretion, we're probably looking at this area right up here where the cold air is at its peak and starting to turn over from warm, turning over into cold, sort of right up here where the vertical upward becomes vertical downward. That's the area of accretion. Accretion is a noun that means basically the process by which layers are added to hailstones. Accretion means to add on new layers and build it up. It's all over in geology. It's also found here in weather. So when accretion occurs, you're adding layers of ice, and basically the updraft air, the speed of that wind blowing upward in the cloud, is the key determiner in terms of how large a hailstone can grow. If you see a huge hailstone the size of a baseball or a tennis ball or cantaloupe, there's hailstones that get that big, tends to be that, of course, the larger the hailstone is, the more wind it would take to keep that up there. But if you were to break through it, you can often see the layers inside. That'll tell you how many times that ice ball had to rise and fall in the atmosphere, adding layers, melting those layers, adding layers, melting those layers, and you get kind of a ring effect. This is what a hailstone might look like in a cross section. If you ever find a big hailstone, if you have to live through a big hailstorm, if you can find the big hailstones laying on your grass or on your deck or something afterwards, grab a few while they're still solid, throw them in the freezer, get them good and frozen, and then later you can melt through partway and see these layers inside. The best way to do this is to take a hailstone out of your freezer and just kind of slide it back and forth across a smooth surface. You can melt it out, melt down one side until it kind of gets a flat edge on it. You could do it on a warm skillet or something, but it melts a little too fast sometimes. So just sliding it back and forth across a countertop or a cookie sheet, and you'll see that the water melts off and gives you a nice smooth surface. When you're about halfway through, you can get the whole picture kind of like this. It's kind of pretty actually, where you get these sort of flower petal shaped rings in there. And basically the different foggy versus clear, foggy clear, foggy clear, each of those sort of has a story to tell, almost like rings on a tree. And so when you see multiple layers in there, that's a single stone that added many, many layers. Another kind of hailstone that you see occasionally is called an aggregate hailstone. What's happened here is many small hailstones have somehow been joined together, cemented to each other with additional ice. And so it's like you've frozen little balls of ice into one large piece. This is the kind of hailstone that if you have to survive large hailstones, you'd rather that they be these kinds than those last ones, because in this case, the smaller pieces are generally somewhat loose, so when it hits something, it doesn't dent your car so much as it might just kind of shatter into many pieces and have ice all over the place. Doesn't mean it can't dent your car, but a loosely adjoined ball of small ice cubes is much less intense and much less solid than a single large hailstone. This is a picture of a hailstone that became very, very large. A typical piece of American currency is around 6 inches across. So this stone was actually 5 inches plus. And the hailstone that you see there has all these pointy sort of edges on it. That's how the ice was freezing on, probably as the water was sort of condensing onto the ice and then began to freeze. It formed these little points. It's a very jagged looking, nasty hailstone. And large hailstones can, of course, damage your house and car. They can hurt you. It's been known to happen where large hailstones can actually kill cattle, humans certainly, but other animals out there as well. My dad grew up, part of his life, spent some time in Wyoming, and would see occasionally stones that would grow in this way and be large enough to fall down and hit cows in the head, hit them in the back and cripple them. Livestock can be severely injured by these because, of course, in the moment of severe weather, most people don't have time to gather all their animals into shelter under roofs, and so it could be the case that a cow or a sheep flock has to spend time outside in a hailstorm and be at risk of being injured. Now, you don't have to copy these numbers down, but it gives you an idea of how much of an updraft wind it takes to create the hailstones you might experience. Pea-sized hail, fairly common. You only need about an updraft of 24 miles an hour. Penny-sized hail, you need 40 miles an hour of updraft. A golf ball, over 60, a baseball, over 80 miles an hour, and if you were to have a softball-sized hailstone, especially those more solid ones, it's got a 4.5-inch size. It's going to take updrafts of over 100 miles an hour. That's incredibly fast. Now again, that's not that you're going to feel a 100-mile-an-hour wind at the surface, but going vertically up into the cloud, the wind could be upwards of 100 miles per hour. And the hail core is the region of the cloud where the storm's hail core will be found, and hail is most likely to be produced and falling through that area of the cloud as well. The hail core is hard to pin down precisely without sending radar signals out and through the cloud. And of course, radar signals are sent out from right here in Bismarck. If you look at the Doppler radar station south of town at the airport or near the airport, the Weather Service has a Doppler radar spinning in what looks like that large white golf ball, sending out signals and cutting cross sections through all those storm clouds in the summertime to see what's inside of them, including possibly signs of hail. This is what a cloud might look like, sliced through the middle. So it's important to notice that here we've got, again, like I showed you in the earlier video, you've got a little cold front line here. That's where the cold and warm air are meeting. And then on this little cross-sectional view, or this top view they call it, you'll notice that cold front is drawn in here, sort of right along here. The blue doesn't show up very well in this picture, but that's where that same blue line is. So this blue line is equal to this blue line. And you'll notice that the light blue arrows in the left picture here are the cold air flowing down and out of that storm. We see that cold air flowing down and out over here as well. So it gives you somewhat your bearings back. So a thunderstorm's heaviest rain there will be very near the front. Heaviest rain surrounded by moderate, surrounded by light rain. And the heaviest rain, that rain core right there, is also the place where the hailstones are most likely to form, in that sort of hail core within that portion of the cloud. One of the features is called roof length downdraft. Roof length downdraft, or RFD as they refer to it on storm chasers, are those cold winds that I mentioned to you in the last video and in the lift source video of air blowing down and out the back of a storm cloud. So I won't go further into those right here because you've already heard those, how they can kick up storms nearby. The next feature is called a wall cloud. A wall cloud is a precursor to a tornado. When you see a wall cloud, the chances that a tornado is right behind are fairly good. A wall cloud forms as air rotates within the storm and begins to extend itself out vertically. Imagine if you take a big log of Play-Doh or something, just kind of roll it on your table. If you start out with a thick log of Play-Doh that's as big as 2 inches across, and just start to roll it across, back and forth, it's going to get thinner as you press on it, but it's going to extend out vertically, or rather it's going to extend out in length at the same time. So when you roll it thinner, it has to get longer. Well, as air starts to rotate within a storm cloud like this, it starts to rotate faster and faster, and it starts to get narrower. It's sort of almost like extending vertically this way as it narrows. And so as it spins faster and faster, it can get narrower and narrower, and that air has to extend out in the vertical instead. And so part of it reaches down to the ground, and we see it as the wall cloud. What happens there is that air is going into this cloud so fast that it begins to condense at an even lower height than before. And usually it has to do with the fact that the cold air that's within the storm and this condensation cold air bodies are extending a little bit to the vertical downward and causing the wall cloud to condense at a lower height than normal. This might be what a wall cloud would look like. This is a little more dramatic than most wall clouds would be, and this is an uncomfortably close picture to where a wall cloud would be. In a sense, it's because a flat part of a cloud grows down out of an already flat bottom of a cloud. And somebody thought it looked like a wall was extending its way out of the cloud. All you're really seeing is you got rotation in there in a wall cloud. And as that rotation comes down out of the cloud, all you see are the straight sides of that area of spinning air. It's like you're looking at a cylinder from the edge. All you see are flat sides and a flat bottom. And as a cylinder lowers, imagine like a large oatmeal can lowering down if someone was holding it up from a distance, all you'd really see is a rectangle, the flat sides, the flat bottom, and it's lowering itself down. That wall cloud looks more or less the same. Here's another one that's got a little bit more of a kind of a pointy base on it, but this section of the cloud here is the normal base, and then right underneath of it here, a little section is extending itself down and out of the cloud. And from that one, if you can kind of make it out here, there's a little skinny tornado that's begun to form its way out of the wall cloud. And again, this explains and talks a little bit about how that goes on. When the cloud's rotating, it's going to form a rope, essentially, that extends its way out. And again, as I said before, imagine you're rolling out that log of Play-Doh when you're a little kid, or if you still have a kid's heart, maybe a little bit more recently than that. Play-Doh's a lot of fun. So if you need to relax, find your Play-Doh. And if you don't have any, convince someone to buy you a few boxes of it when you get to the next stop at Target or Walmart. You know, some Play-Doh to veg with. Nothing makes you feel like a kid like playing with Play-Doh. Eventually, tornadoes can kind of come out of those storms. You know, what you see here on the left is a very, very thin tornado. They would be described perhaps as like a rope of a tornado coming out of it. On the right, a fairly small little tornado as well. But tornadoes, I'll show you some more pictures of here in a moment, occur when funnel clouds come out of a wall cloud most of the time and reach the ground. So if a wall cloud could be followed by a funnel cloud, which is that narrow point. And we see that really quite well on the right side of this picture, but also on the left, these white sort of funnel clouds reaching out of the storm. If they reach the earth, then they become tornadoes. So a funnel cloud forming out of a tornado, or rather forming into a tornado if the conditions are right. Funnel clouds are typically white because they're simply condensed, or usually we'll say condensed moisture, and that's really all. When they get dirty and darkened, it's because they've picked up dirt off the surface, and so we get white if they've been only funnel clouds. But once they touch down and become a tornado, the easiest way to be sure is if there's dirt and other debris being sucked in from the ground and drawn into that storm. Compare that little tornado, that tiny little tornado at the bottom, to the size of this huge thunderstorm as a whole, and this little tornado is what we're most afraid of. Now, granted, tornadoes can be amazingly destructive and deadly, but when you think about how small they are by comparison to the rest of the storm, they're really just a little needle almost sticking out the bottom, even a big tornado compared to what it's coming out of. Tornadoes are often measured by the damage that they cause and the wind speeds that are observed, and they're ranked on what's called the Enhanced Fujita scale, or the EF scale, all the way from 0 to 5. This picture shows a substantial tornado. I'm not sure which way it's moving. I hope it's moving across behind those trees and not toward this little house. But this is often the case where a tornado can be very close to you. And if you were sitting on the porch of this house, I would imagine that you would hear the thunderstorm roaring just a few miles behind your house. This shows the values for the Fujita scale and then the Enhanced Fujita scale. You don't need to copy these down and memorize these either, but they're there just for reference to kind of give you an idea of some of the information that goes with each of the storm intensities. The Enhanced Fujita scale is a little bit more accurate version of the original older Fujita scale. Today we would use the EF scale pretty much exclusively, and those values are more accurate in predicting the type of storm or the intensity of thunderstorm and tornado that you're getting. Remember I told you in the last video that, or the first video, that Florida is the key to finding the most thunderstorms. But for us, we want to look at tornadoes in this. The most common regions for tornadoes to form are shown here in yellow, and then more common in orange, and the most common of all in red. So basically that's Tornado Alley is right up there in the southern plains. This is where we find the most tornadoes. Again, keyword being most tornadoes. Every state in the union by now has experienced a tornado, and so as we look at the U.S., there's some lighter tan colors up into Bismarck on this picture. And below that, you have to go quite a distance before you start getting to areas where the thunderstorms are more likely to produce tornadoes. The conditions are just right down there. And again, because tornadoes come out of thunderstorms, the same ingredients are still necessary for a tornado to be there at all, because a thunderstorm has to get underway first. That warm, dry air from the desert southwest and that warm, moist air from the Gulf of Mexico can come together to give us just the right ingredients, and the place where that happens is the southern plains. Now, this is the final graphic I'll show you, and that's showing and contrasting the idea of here's Tornado Alley, Texas, Oklahoma, Kansas, Nebraska, up into Iowa. These are considered the Tornado Alley states. Yet this graphic actually shows the likelihood of dying due to a tornado as being somewhere east of Tornado Alley. So, question then, why? What factors make death more common east of Tornado Alley than actually being in Tornado Alley? Well, the key is time. tornadoes kick up and form in the afternoon into the evening across the tornado alley, and that's why you see those guys out there recording them. It's much easier to record a tornado on video if there's some sunlight behind it or lighting up the sky so that you can actually make them out. You notice though on this picture that this describes and shows the places where the chances are most likely that you're going to get a tornado after dark, a nocturnal tornado or a nighttime tornado. Notice how likely that is in places like Arkansas. Down here, Arkansas is showing 42.5% of all tornadoes are nocturnal, almost half. Tennessee, 46%. That's basically half of all tornadoes happen after dark. And slightly north of there in Kentucky, 41.5%. So in these three states, almost half of all tornadoes happen after dark. And those are more deadly because people are asleep. That's the real simple truth. When you're sleeping during a tornado, or when the warnings are sounded, you're much less likely to actually hear them. And so there's going to be a greater chance that you'd actually miss it and perhaps die. There's also a great amount of poverty in most of these areas. Arkansas is one of the poorest states in the United States, and this whole south, deep south, is a very poor region. What this does is sort of save those storms till after dark as they move out of tornado alley to the east, and then they strike areas where it's dark, people are sleeping, and many people live in very poorly built constructions. So trailer homes or old houses are much more likely to be destroyed by a tornado, and if what you're sleeping in is destroyed, you're more likely to die. It makes good sense. As far as being likely to be killed by a tornado, if you're in a solid basement, your chances of survival are great. But if you're living in a trailer home where you're sleeping and there's no basements, chances of death pretty substantial. So that poorer population and the fact that when you're sleeping you can't hear sirens nearly as well help us to understand some of the reasons why. So if you're going to get down some information on this slide, you might want to pause it, jot some things down, and then continue on from there. That's it, folks. When we're looking at thunderstorms and tornadoes, there's lots of information to be had. I hope you've had a chance to get all these notes down. If you haven't, please finish them up before you do anything else, including the online simulation from the National Geographic page. Or moving on next week as we look into storm chasers and a little bit of an example of the work that they do and some of the reasons why they do what they do. Thanks for taking all the notes, and I'll see you soon.